Welcome, everyone. Thank you for taking the time to join us for this webinar session. My name is Dennis, and I will moderate today's webinar with the subject Crystal Structure and Nano-voids, two major factors that influence blind microwire reliability. First and foremost, I would like to introduce to you Roger Messi, who is our speaker and subject expert. With more than 27 years of experience on PCB fabrication and its challenges, Roger became one of our leading experts with deep knowledge on how to influence BMV reliability to your favor. His expertise helped us to reach tremendous progress in this field and continue to expand our leading position in providing highest yield products. A couple of words about the webinar. The webinar will be divided into two parts, 40 minutes presentation and 15 minutes Q&A session. I encourage you to raise questions from the beginning of Roger's presentation and therefore to use the Q&A function, which you can find on the top right corner of your screen. Your questions will be visible only to me and Roger. Therefore, do not hesitate to ask any related to the topic questions. We'll try to cover as many questions as possible during the planned Q&A session at the end of the presentation. If the time allows, we will answer all questions right away. Also, Roger will be available after the webinar to reach out to you via email. Last but not least, if you face any technical issues, please make sure to enter the webinar via the latest versions of Chrome or Firefox browsers. Now let me hand over to Roger. Please enjoy the session.
Okay, thank you, Dennis. And good morning or good afternoon or good evening to everyone, depending on where you are in the world. So as Dennis said, today we're going to be talking predominantly about factors affecting microwire reliability and looking more specifically at crystallography and recrystallization and nanovoid formation within the microwires themselves. Wrong button. Okay. So I'll start off with a relatively straightforward introduction before we go into the main subject. And I'll start with recrystallization. And while I'm focusing in many ways on the electroless coppers, I will also discuss how this potentially affects the electrolytic systems as well. I'll then follow that up with some classifications and some explanations of nanovoids, because this ties in quite well with recrystallization and especially how they potentially can affect microwires as well. We'll then do a small case study looking at solution flow, because this is definitely something that can in fact affect recrystallization and voiding. And then there's a summary, and then, as Dennis said, we'll open the floor up to Q&As as well. So if we go back, I don't know, maybe 20, 25 years, probably before that, when the first microwires were developed and produced, it's probably reasonable to assume that 2 or 3 days after the first guy made his first panel with wires, a couple of days after that, there was somebody else hunched over a microscope trying to work out why all those wires failed. Things have moved forward. We now make hundreds of millions of laser drilled wires a day instead of hundreds. And the defect rate is no longer 100%. It's certainly much lower than 1%. But we still have an appreciable level of defects within microwires. And while we are gaining a lot more information and experience on them, the level of concern within our industry has steadily increased. So much so that 2 years ago, IPC released their white paper, which probably most of you have read already, where they really highlight concerns regarding wire reliability. And that's essentially brought us to where we are now, where there's a lot of companies, both board manufacturers, chemical suppliers, test houses, are looking at wires and trying to understand design criteria that affect them, whether that's dielectrics, staggered wires versus stacked wires, layer counts, the works. So there's a lot of papers looking at design characteristics. There's equally huge numbers of papers, some from ourselves, looking at failure and trying to learn from dead bodies, looking at failed wires to try and understand things. But the one thing that is coming out in everything we've read and everything we're doing is microwire reliability is a very, very complicated subject. There's a multiple of factors which affect it: design, manufacturing, processing, as well as material characteristics. And leading on to materials, which is where essentially we're going to be looking at predominantly for most of today as well. So if we move into recrystallization, if you look at microwires and you cross-section them, typically you're going to see one of two types of crystal structure. The ideal structure is the one that's currently on the screen. And this we say is ideal is because there's no crystal boundaries between the target pad and into the electrolysis layer and into the via fill copper either. So metallurgically, it appears to be a single material. Okay. So because it's a single material, there's no alignment of grain boundaries. So any crack path has to be quite convoluted in that it has to follow through the entire crystal structure. And this ideally is what you would want your microvias to look like when you section through them. Because it appears to be a single material, it's going to have the best mechanical properties available to that. So this is utopia in terms of what a microvia should look like. Unfortunately, quite a lot of vias also look like this one. And here you can see quite clearly the crystal structure in the target pad is dramatically different to that in the via fill layer. Yeah, so there's very clearly a dislocation between the crystal structures. And that dislocation is usually centered around the electrolysis layer. However, when you look at it close enough, it can actually be between the target pad itself and the electrolysis layer, or it can even occur between the electrolysis layer and the electrolytic. So we have to keep in mind that there's actually two interfaces within a microvia structure. And this dislocation can occur at either of them. Metallurgically, this has to be a weaker structure. And the reason why I say that is you can see the grain boundaries essentially are lining up. There's certainly more images following where that alignment is a lot more clear. But it's a much easier crack propagation path to just run along a bunch of aligned grain boundaries. So while a single crystal structure gives you a good or anticipated good reliability, the structure as you're currently looking at is likely to give you a reduced reliability. So this is ultimately what we're trying to avoid in terms of crystal structures within microvias themselves. So if we look at mechanisms, how these can potentially form, and what you're looking at here is a sample where we started with the copper substrate, we deposited the electrolysis copper, we then put the electrolytic on the surface, and then immediately after plating, we quenched the entire sample into liquid nitrogen. So we freeze the crystal structure as soon as physically possible after plating. And this gives us a couple of advantages. The first thing you'll notice is the electrolytic layer is deposited as a very, very fine crystal structure. So essentially it has no crystal structure, it's so fine. When you section the picture, as we saw earlier, there's quite obviously a crystal structure there, it's big and it's visible. So some degree of recrystallization has to occur. And the same can be said for the electrolysis layer. And what you can see looking at the image here is the electrolysis layer deposits first. If it's a good clean interface between the electrolysis and the copper substrate underneath it, the electrolysis will begin to recrystallize and it will adopt the crystal structure underneath it. And as you can see where the arrow is, you can see the single grain, the lighter gray, is passing into the electrolysis layer. This is what we term epitaxy ultimately. You can also see that above that is the electrolytic layer, and the grain has continued to pass through that. So the recrystallization wave, or the diffusion front, I guess, starts in the substrate, comes through the electrolysis layer, and then passes into the electrolytic layer. And this is why we've termed it as a bottom-up recrystallization, because the layer takes the crystal structure from the one underneath it. In order for this to occur, the interfaces between each of the layers have to be physically clean and chemically clean, because there are defects within the structures which can potentially pin that diffusion flow through the structure. So they have to be clean in order to get unhindered grain boundary diffusion. So when we see a fully bottom-up crystallized structure, which we'll see in the next slide, it's a good indication that the process is running optimally and all the interfaces are clean and in the best physical condition possible in order to plate and also to recrystallize. What we're looking at now is essentially another sample from the same group, where the image on the left is the frozen structure quenched in liquid nitrogen immediately after plating. The image to the right is what happens when you take that sample out of the liquid nitrogen and allow it to warm up, and then you anneal it to force the crystallization to occur. And again, as with the earlier examples, you can see very large grains that start in the substrate material, pass through the electrolysis, and pass into the electrolytic layer. So there's no discernible interfaces anywhere across that structure. You can't identify clearly where the electrolysis layer is. You have to use a different technique in order to determine that. Because there's no discernible interfaces, there's no alignment of grain boundaries. So any crack has to go through a much more tortuous crack path in order to fail and to propagate. As I said earlier, we can only generate this structure if there's very low levels of contaminants at the interfaces within the structure, so the process is more than in control. And because it's the best crystal structure, we would expect a high level of joint integrity. Okay, so this is the realistic mechanism how crystallization can occur and does occur under optimum conditions to give us the optimum joint reliability. Conversely, we have what we call a top-down crystallization mechanism. And these two images are exactly the same as the previous ones, except quite clearly, after the sample is frozen on the left, there is no bottom-up recrystallization occurring whatsoever. There's no penetration of grains through the electrolysis layer and into the electrolytic. Something is either physically stopping it move, the diffusion boundary, or it's chemically pinned by contaminants within the structure itself. If we move to the image on the right, where this structure is allowed to recrystallize, again, you can see there's the odd area, maybe here, where there is a degree of transfer through, but generally there is still a very clear discernible layer where this target pad stops and the plated layers deposit. Because of that, whether the arrow is to the right, you can see there's essentially a single grain boundary running across the middle of that joint. This is likely to act as a crack propagation site and therefore is more likely to lead to low levels of joint integrity. And the way we associate this chemically is that there is a high level of organics and contaminants within the structure as well. Okay. What we're looking at now is some samples that we ran with a customer in China, where we were trying to determine crystallography and how the impact of that is on physical properties as well. So the two images at the top are samples as plated, where crystallization has been allowed to occur. And the images at the bottom are similar samples, but they've been through 6 times reflow cycles. And at this point, all of the interfaces passed and all of the joints passed electromechanical testing after reflow cycles. The image on the left is a standard SEM image. And what's interesting with that one is you cannot see the chemical, the interface between the substrate layer and the plated layers. Okay, so it's a bottom-up recrystallization structure. The two images on the right show you essentially the crystal orientation within the grains within the structure. So everything that's green has the same crystal orientation as everything that's blue and purple and so on. And what you can't see again there is any alignment of grain boundaries. So this bottom-up recrystallization mechanism is truly random based on the substrate underneath it, but it's giving very good joint reliability in terms of thermomechanical performance of microvias. If we now take a look at a top-down system, and if we start at the top, you can see in the image to the left, just under the red line, as I can draw it about there is an alignment and a clearly discernible interface. And if you look to the backscatter image on the right, you can see very clearly there is an alignment of grain boundaries. So there's almost a horizontal line running across the middle of that sample, where the crystallization is being inhibited from the substrate through to the plated layer. Following thermal reflow cycles, where it has to be noted, all of the interfaces failed, 100% failure in these samples. And looking here, you can see quite clearly there is a crack formed, And that ties in very nicely with this alignment of grain boundaries due to failures in crystallization transfer. So by the time we'd finished these tests, we determined mechanisms by which bottom-up and top-down crystallization could occur. And then we'd proven, at least to ourselves, that where you get breaks in crystal structure, there are definite reliability concerns within final structures, because that grain boundary alignment can potentially act as a fracture path, which makes failure dramatically easier. I mentioned mechanisms, and with the next 3 or 4 slides discuss essentially how crystallization can occur and some of the factors affecting that. The 2 easiest ones to explain, fortunately, are the ideal one and the absolute opposite. So we'll start with a full bottom-up recrystallization scheme. So this one's easy to explain because everything does as you want it to do. The schematic at the bottom shows it sequentially in that you start with a target pad, which is chemically clean. There's nothing physically on the surface, and there's no organic contaminants on there either. The electrolysis layer becomes deposited in its fine-grained structure, as we saw through the SEMs earlier, and then it begins bottom-up recrystallization, taking the epitaxy from the substrate itself. The electrolytic is deposited on top of that, and this also recrystallizes in a bottom-up manner, so you get the single crystal structure as we see in the fib cut on the right. Typically, we see that thinner electrolysis layers, and by that we mean typically 0.5 micron and less, are more susceptible to bottom-up crystallization than thicker layers. And this is because the thinner layer will recrystallize faster because there's physically less of it. So we intimate from that a horizontal process potentially will give us better performance relative to others because we need much thinner layers of electrolysis copper within that. If we now look at a total top-down system, so here the dislocation pattern occurs between the target pad and the electrolysis copper, so essentially at this area. Excuse me. In order for this to occur, there's a couple of mechanisms, but the easiest one is there is a physical barrier occurring on the target pad which stops the diffusion front passing through into the electrolysis. And the most common one of these can either be very, very thick oxide layers on the target pads, or residues from such things as incomplete desmear or modifications or melted coppers from laser conditions as well. So if we look to the schematic at the bottom, you essentially start with a target pad which is physically contaminated. So there's something on the surface, whether it's an oxide or residue from poor smearing and incomplete cleaning. The electrolysis is deposited. Because of that barrier, the recrystallization front can't move, so it's pinned. So the electrolysis doesn't recrystallize. It stays as the fine grain in its as deposited state. The electrolytic is then placed on top of it, but there's a good interface between those 2 layers, so that as the electrolytic begins to crystallize, the diffusion front passes from the top down into the electrolysis layer. So as you can see from the SEM, the electrolysis has adopted the same crystal structure as the electrolytic, but not the same as the substrate material. So a total top-down system based on contaminants prior to electrolysis plating. The next one is where it starts getting a little bit more complicated because the electrolysis layer does a bottom-up recrystallization, but the electrolytic does a top-down. So the boundary has shifted away from the target pad and is now between the electrolysis and the electrolytic. 2 potential mechanisms that we have for this, which we've tested and both seem to be valid. The first one would come from what we term as a wet, dry, wet process. So your panel comes out of a wet electrolysis copper, it's then dried, it's left in storage for a period of time where it will oxidize, and that then goes back into a wet process, so the cleaning phases of your electrolytic plater. That oxide is much more robust and is less likely to be removed by the acid cleaners, so that it then acts as the physical barrier to stop the diffusion passing through that. So for this reason, the electrolysis will bottom up diffuse, crystallize, it will hit the oxide layer and the boundary stops, and then the electrolytic top-down crystallizes as well. So that's one way it can happen. The other thing that can happen potentially is if the bath isn't in its optimum condition, or there's something strange going on with the additive system, you can get an excess of co-deposition of the additives. And by that, I mean, we obviously put a multitude of components into the electrolysis bath. It's not just copper and formaldehyde. We put grain refiners in there, we put bath stability agents in there, and they all potentially can co-deposit into the copper layer itself. If the bath is out of control, for want of a better term, you can get an excess of those additives depositing into the bath itself. So what happens is, as the bottom-up diffusion occurs through the electrolysis, that diffusion wave collects and pushes all of those additives through in front of it, to the point where they then collect at the top of the surface as well. Okay. When they're at the top of the electrolysis, they then begin to act as the pinning agent to stop further diffusion. Because there is also a high level of additives at the surface of the electrolysis, we then see a higher co-deposition from the electrolytic additive system as well, which further pins diffusion so that the electrolytic then plates top down as well. Okay, so physically, it would look very similar to the previous case, because unless you know exactly where your electrolysis layer is, but physically, actually, the diffusion has gone through the electrolysis layer and then has been pinned at the grain boundary system before the electrolytic system as well. And the final one is basically a combination of the previous two, in that the electrolysis will deposit and then begin a bottom-up recrystallization scheme. And then at some point, the additive concentration becomes so high that it becomes, the diffusion wave gets pinned within the electrolysis layer itself. So the diffusion stops in the middle of the electrolysis, and then the electrolytic recrystallizes, in a downward manner. So the interface actually arrives in the center of the electrolysis layer itself. We don't see this one incredibly often, but we do see it. And when we see it, we typically see it in thicker electrolysis layers. So if you're approaching a micron or up to 40 microinches, you start getting into the arena where this diffusion mechanism can stop in the middle of the electrolysis copper layer itself. And as we said earlier, anywhere you see a dislocation in crystal structure is a potential weakness within the overall via itself. Okay, so that's the primary four mechanisms that we have in terms of crystallization. The next one should just be a summary. Yeah. So what we're saying is, ideally, you want a fully bottom-up recrystallized microvia structure. That single crystal structure across the target pad and into the plated layer itself. In order for that to occur, it's suggesting that the process is well controlled and that all the interfaces are clean, because there's a very low level of organics within the plated structure itself. Going from a wet, dry, wet process increases the risk of contamination. So a wet to wet is always a more preferable solution. And we see that thinner electrolysis layers are much better in terms of achieving this bottom-up crystallization than a top-down system that we get typically with thicker ones. Moving out of the electrolysis layer a little bit, we also have to be aware that the electrolytic baths can have an impact on crystallization as well. They are also prone to additive co-deposition, which can pin crystallization within the to the edge or within the electrolysis layer itself as well. So it's pretty critical in determining where the crystallization boundaries occur when you have them, because it's going to indicate potentially where in your process and your production routes we have to start looking in terms of troubleshooting. Okay, so relatively simple subject in terms of crystallization, but there's a lot of complex things potentially going on within that itself. So if we move on to nanovoids, the usual question that we first get asked is, okay, so what's a nanovoid? We used to have voids, and then someone discovered microvoids, and we've now discovered a nanovoid. So it's purely a matter of scale. We've arbitrarily identified nanovoids as features 10 nanometers or smaller, or around that sort of ballpark. And as you can see in the image on the right, there's an electroless layer which is about 400 nanometers in depth. And to the left of that, you can see a cluster of voids where the total depth of that void bath is probably about 100 nanometers. So they are very, very small features. The second question we usually get is, okay, are they new, or is it just something we've now detected because we've got better tools? I don't think we'll ever really know the answer to that one, but I would imagine that they've probably always been there. And as your ability to produce boards has improved and our ability to produce better chemistry has improved, that's allowed much more difficult designs to be developed to the point where nanovoids have had to be detected because there are concerns whether they have an impact on reliability. And as we know from microvoids, if they coalesce, they fail. So the expectation is nanovoids are a concern because we will get void coalescence. And if the voids coalesce, they grow, and we then get a critical fracture path. And because they quite often occur at the interfaces, which we were discussing in recrystallization, if we have an alignment of voids with an alignment of grain boundaries, that is almost certainly going to fail preferentially to the rest of the crystal structure. In terms of detecting nanovoids, because they are small, we use a variety of tools within Atotech. Like many, we start with an electron microscope. SEMs are fantastic tools, and a number of PCB plants even have their own SEM work now. The benefit of a SEM, obviously, is high magnification, high quality with a good depth of field, but it's limited in that you can only look at one plane. So the image to the top left, this one, you can only see in the SEM what you can see in that image. You can't penetrate into the structure. And this is why we started using the focused ion beam, or the FIB. The benefit of a FIB is it allows you to cut into the sample that you're looking at. So you etch in, you ablate a perpendicular line into that to create a structure, which you can then look across, which is essentially what we're doing here. We can look along and into the depth of that crystal and across that crack failure as well. With FIB, we get a fantastic idea on crystal structure because it creates a really nice, clean image without few preparation artifacts that you typically get through polishing. One of the strengths of FIB is it's supported by all the SEM analysis tools, but that is also one of its weaknesses. Because the beam penetration in a FIB system is quite deep and you're penetrating into a thick sample, you always detect copper, and you always detect a lot of copper. So you have a very high background count, which then means it's difficult to detect very thin layers or very low atomic mass materials or very fine dispersions. So its strength is its weakness, but it is a fantastic tool for failure analysis. But unfortunately, it limited us in developing our knowledge around recrystallization and nanovoids especially, which is why we moved to a transmission electron microscopy system instead. With a TEM, you essentially, as the image here is showing, you use 2 FIB cuts to create a very thin sample. These things are about 60 to 100 nanometers in thickness, which you then break out and then put into the TEM unit. And because it's a thin sample, you get very low background counts of copper. So it's a lot more sensitive in terms of elemental analysis. We can detect very low atomic mass materials, and we can measure quite typically very low dispersions as well. So it's a really sensitive tool which taught us an awful lot about what's going on within a system. The other benefit of it is because there's less scattering in the sample, it has a much finer resolution. So we're certainly working less than a nanometer, so which is well within the capabilities of the materials that we're looking for. So we found TEM to be an incredibly powerful tool and a pretty essential tool if you really want to try and understand what's going on within the structures themselves. So if we look at this as an example of one of the major light bulb moments, I guess, from a TEM analysis, if we start in the top left, you can see the target pad is off to the right and the plated layer is in to the left. Somewhere in the middle is the electroless layer, but there's also a band of voids lying within that structure. It would not be unreasonable to assume that those voids are in the electroless layer. it would kind of make sense. The location's about right. If we move to the image on the top right, using a TEM, we can actually quite often detect the palladium catalyst layer itself. You can't do this with an SEM or a FIB. You physically just can't detect the palladium at such a low level. Because we can predict it, we can detect it, we know where the electrolysis layer starts, which is pretty good in terms of identifying potentially where those voids are located. A lot of our electrolysis baths contain nickel. We use it because it gives us a degree of control over the physical properties of the deposit. But in this case, we can use it as a tracing element to determine the thickness of the electrolysis layer. And by that, we can fix its position. And that's exactly what you're seeing in the bottom right-hand image, is the location of the electrolysis layer itself. So if we now superimpose all of that onto the image on the bottom right, what becomes apparent is the voids aren't actually in the electrolysis layer at all. They're in the first 200 nanometers of the plated layer. So if we'd gone on the first example only, we would have spent months troubleshooting an electrolysis process where potentially we should have been looking at electrolytic layer. And this was quite useful for us because we also had the same opinion. Microvoids are associated with the electrolysis copper layers, and blind via reliability is impacted by electrolysis copper layers. Yes, it is, but it can also be impacted by the electrolytic processes as well. So with this in hand, we then started trying to characterize as many of the microvoids and nanovoids that we were seeing, and we were able to classify those into 6 different types. I think it's 6. The first one is one that we class as thermally induced because you cannot see it immediately after plating. So post-plate, the structure looks perfectly good. If you then go through some form of thermal heat treatment, whether that's a reflow cycle, a pressing cycle, or just thermomechanical testing, voids become apparent. And what was interesting with a lot of the voids that we were seeing in many of those classifications is there is no impact on bottom-up recrystallization. So metallurgically, the structure looks great, but at a higher magnification, you start to see bands of voids within that structure itself. So no epitaxy changes, fully crystallized from the bottom up. In this type of void, what we were seeing is a thin band of voids. So it's not a single line, it's a small cloud, which were located right at the interface between the target pad and the electrolysis copper. So it was something was affecting it very early on in the electrolysis process. Using the TEM, because we couldn't detect anything with a FIB, was what we were determining was those voids were often present or surrounded by areas of increased palladium content. Now, obviously, source of palladium is going to be the activators from the electrolysis process. And what we determined in the end was the palladium systems are prone to precipitation. They agglomerate and they precipitate. It's a dynamic bath. It's constantly changing. Those agglomerates will absorb onto the surface of the panels themselves. So we end up with palladium nanoclusters spread randomly across the panel. Hydrogen and palladium have very high affinity for each other. So high palladium is going to give high adsorbed hydrogen at that structure as well. During the heat treatment cycle, that hydrogen is released back out of the structure, and it can potentially form gaseous hydrogen itself and create a bubble. But what's more likely to happen is it will reduce any oxides that are present in that structure, produce water vapor, and then we get the void. So this thermally induced system, we tie down to adsorption and precipitation of the activators and then reduction of copper oxides. That's the only one we've been able to identify that's thermally induced. Everything else is visible after plating and recrystallization. So for this, we class them as plating induced. And the first 2, I think it is, have a similar mechanism to the previous in that it's a hydrogen reduction of a copper oxide layer. But how that oxide forms varies ultimately. So this type, again, no impact on bottom-up recrystallization, but instead of a cloud of voids, it's a single line of voids. And it's usually, again, around the interface between the electrolysis and the target pad. And what we believe this one is associated with, and it's one of the ways we've been able to create it, is this very thick oxide layer that can cause recrystallization to be inhibited. If that layer is thin enough, it won't inhibit recrystallization, but it will be sufficient to create voids when it's reduced by the hydrogen that's absorbed into the electrolysis layer as well. So poor cleaning at the first stages of the electrolysis process is insufficient to remove that oxide layer, and therefore it comes back out of solution, and then we get the void. The two TEM images to the right essentially are testing this theory out. If you look to the one on the left, the band of voids are forming at the interface where we'd expect. When we do the TEM analysis, we do see a high level of oxygen at that interface, and they are cognizant with the voids. We deliberately set a bath up where we had much lower oxygen contents within the bath itself, and in that case, we got no oxygen at the interface, and we similarly had no voids. So that mechanism played out in terms of a robust oxide, which was getting reduced to create the defect itself. The next one, again, a very similar mechanism, but we can associate this one with fluid dynamics occurring within the microvia itself. Again, no impact on bottom-up recrystallization. In this case, again, we start to see a band of voids directly at the interface between the target pad and the electrolysis layer. And there's two potentials that we could find this one to occur by. The first one is if there is a very low level of solution exchange in the microvia. You can essentially, at that point, you're not replenishing the chemistry sufficiently speedy that you're maintaining a good copper concentration. So the tiny volume of liquid in the microvia while plating is essentially becoming depleted of copper. Because of this, the bath essentially at that tiny volume isn't depositing correctly. So we get an artificially high level of nickel deposition, and that associates, it tends to bring a high level of absorbed oxygen with that as well, which is what we're seeing at the image on the left. We're seeing a higher level of nickel in that area because the volume is decreasing at the base of the microvia, and we're not replacing the chemistry fast enough. And similarly, we get the associated high level of oxygen with that as well. So if the solution flow is very low, we get an artificially high oxide and nickel content, which is then subsequently reduced. Conversely, if the solution flow is too aggressive, you essentially get nanocavitation within the microvia itself. So you're getting air bubbles entrapped within the solution, and you essentially oxidize the electrolysis while you're plating it. And we've certainly been able to recreate that, which is what the image on the right is showing. You can see the very high oxygen spike in the TEM analysis, which then tied in nicely with the location of the voids that came post-plate as well. Looking back, we can hold our hands up and say our early cyanide-free baths were prone to this, we discovered, once we knew what to look for. But in the more recent versions of the cyanide-free baths, we've corrected for that. So the cyanide-free baths now have similar levels of propensity of this to a non-cyanide, to a cyanide-containing bath. Moving away from reduction of copper oxides by hydrogen, we start now looking at the target pads themselves. It's the biggest area at the bottom of the microvia. It has to have some impact as well, and it certainly does. And what we found in this case was the roughness of the target pad can essentially disrupt the deposition of the electrolysis copper itself. In the way that you can get high current densities areas in electrolytic plating, what we believe is happening is the high spots on target pads essentially act as accelerators for electrolysis deposition. And because they're accelerating the deposition mechanism, they do so in an uncontrolled manner. So we're getting uncontrolled deposition of electrolysis, which leads to nodules, which is what you can see in this image. We start seeing a buildup of nodules on target pads. And because it's an uncontrolled deposition, those nodules quite often contain voids. So this is more of a physical relationship from the target pad leading to an electrochemical, essentially electrochemical deposition within the electrolysis system as well. Again, the early cyanide-free baths were more prone to this. Again, it was corrected within the more recent baths. But it's something that we have to seriously consider. Is the target pad, as I said, is the base of your via. That surface has to have an impact in terms of laser quality, how that recrystallizes potentially the copper structures during laser drilling, and then cleanliness of that pad and the roughness of that pad, because these all can potentially affect the way the electroless coppers deposit and recrystallize. Moving on to the final types, and this is where we now start looking at defects occurring within the electrolytic layers. What we found in this case was bottom-up recrystallization through the electroless layer, and then a band of voiding occurring within the first half micron of the electrolytic layer itself. And what we associate this one with is co-deposition of the plating additives themselves. So at the initial phase of electroplating, we obviously need to initiate that mechanism. So it's a much more aggressive pulse cycle, essentially, compared to the rest of the baths in some ways. And that can lead to enhanced co-deposition of plating additives. And that's essentially what the image on the right is showing. Where line scan 1 was taken, there's no voids, which is great, because we then get the nickel spike identifying, which is the green line, identifying the location of the electroless copper layer. We then went looking for chlorides and oxides, because these are typical additives that would co-deposit, especially the chloride. And we didn't find particularly high levels of those. So low levels of adsorption of those additives didn't lead to voiding. If we now look at line scan 2 underneath it, where there's quite clearly a band of voids, in this case, you can also quite clearly see higher levels of chlorides and higher levels of oxides. So in the initial phase of plating, we're getting an increase in co-deposition, and that is going to be sufficient potentially to pin grain boundary diffusion, but it's also potentially sufficient to lead to void failure, void generation as well. I do hasten to say that this is a low level of incorporation in this case, but unfortunately, there is another system which is exactly the same mechanism, but the co-deposition is much higher, to the point where you definitely do get a break in epitaxy. So you pin the grain boundaries to stop the diffusion coming through, and you then see, as you can see in this image, you see the band of voids forming on top of the electroless layer and prior to the electrolytic plate. This high level of additive co-deposition is the only mechanism we've seen that leads to a break in crystallization, bar physical boundaries, which we discussed earlier on. So when there's a break in crystallization, the second action after determining that should be look closely at that to determine, is there a higher level of additive co-deposition, in which case we need to start potentially looking at the interactions between the electroless layers and the electrolytic layer itself. And that's the 6 types of voids that we've classified. Some of them are associated with agglomerates from palladiums, and potential corrective actions for that. Aditech have always advocated the use of the ionic activation system. We get a much finer dispersion of the palladium. It's less prone to agglomeration compared to the palladium tin colloid systems. And we've also now introduced pre-dips, which are more compatible with the ionic activators. They stabilize the baths better. They reduce the agglomeration, they reduce the precipitation. And those customers who are running it are definitely saying they get less palladium-related defects within their products. For the 2 mechanisms where it's reduction of oxides, essentially you need to start looking at reviewing your cleaning procedures and the way that those cleaners and the chemistries are delivered into the panel. So Aditech obviously advocate the use of the uniplate horizontal plating tools, because we get much better solution control. We can treat every panel in exactly the same way, and we get better fluid delivery into the base of the microvias where it's essential. The other thing to bear in mind is the age of your electroless copper process. Copper baths have improved massively in the last 5 to 10 years, at least, certainly within the last 2 to 3 years. If you're running an older copper bath, you will see technical benefits from adopting or at least reviewing the newer baths that are available. We certainly have developed them with Nano-voids in mind, and they offer improved throwing power, improved bath stability, and improved resistance to nano-voiding as well. Moving into the additive co-deposition defects, really this is a very case-by-case event. There are certain electroless baths we found are compatible more with other electrolytic baths and vice versa. So it has to be done hand in hand to look at the additive deposition and potentially also the impacts of that with the electrolytic baths as well. A summary that I mentioned earlier on regarding solution flow, because we discussed that a couple of times. This was again done in China, comparing a horizontal process ultimately with a vertical process. And what we were looking at was recrystallization in vias. And we started by looking at the top. So here we're looking at the capture pad at the top of the via itself. Solution delivery is very good. And we see full bottom-up recrystallization in a production-ready vertical line. Yeah. No nodules, no voids, so perfect structures. However, when we move to the bottom of the microvia, the solution delivery isn't as good. We start to see a change in the structures. We're beginning to see nodules forming on the electroless layer because we're not replacing the solutions sufficiently fast enough. We're suffering from bad solution flow, and we start to see breaks in crystallography. We can see a dislocation within the structure between the target pad and the plated layers. So we're not getting bottom-up recrystallization because we're not in a position to clean and guarantee that structure is technically good. In the image to the right, we're starting to see voids forming as well. So while there are a lot of microvias made vertically and they are reliable, we are definitely concerned about the capability limitations of vertical processing because we're seeing more vias where there are breaks in crystallography and there are breaks in voids. So we anticipate increased failure risks in these crystal structures as well. Moving to a horizontal process, much as you would expect from a tech person, it's perfect. Typically we get very good crystallization. We get good solution delivery. We're not seeing a high level of voiding. And because of all of those, we're giving the best opportunity in terms of via reliability as well. So while I mentioned solution flow, we've now got enough data to say that actually it is important. It leads to mechanisms, and we can definitely see benefits from one versus the other. So moving on to the summaries. In terms of recrystallization, bottom-up recrystallization is your best shot in getting the best via reliability. In order to achieve that, you have to have clean chemical surfaces and processes that are running in control. If you can minimize any chance of oxidation, so never let your board dry out, you will get a better performance, in terms of plating recrystallization. And we see thinner electroless layers perform better than thicker layers as well. We have to acknowledge that both electroless and electrolytic baths do give a degree of co-deposition of the plating additives. This has to be monitored or at least looked at periodically and taken into account when we're looking at nano-voids, because this can impact recrystallization and it can then impact via reliability as well. But the aim ultimately is a bottom-up recrystallization scheme. Moving to nano-voids, they may be something new. I don't believe they are. I think we've always had them. It's just we're now aware of them, and technology shifted to the point where they are a going concern. We've started to identify and classify them, and most of them, fortunately, don't impact recrystallization. There's only really one which does, and that tends to be a really out-of-control process in some respects. Those voids that form are on a nanometer scale, so they are tiny, but voids coalesce. And when they coalesce, they grow. And as things grow, they are more likely to act as crack defect points. As I said, the co-deposition has to be taken account in exactly the same way as it does for recrystallization. And we are slowly building a case that horizontal processing gives better performance in vertical cases. We see better performance in terms of recrystallization, and we're seeing better performance in terms of feedback from customers running horizontal processes as well. Last slide, almost. As I said earlier, it's a very complex relationship. Everything has to be not quite perfect, but pretty darn good in order to get a reliable joint. Interfaces have to be clean. Your electroless copper bath has to be in control and running correctly and optimized and run. Similarly for electrolytic, because both of those can lead to co-deposition, and impurities in the bath can potentially lead to impurities in the layers, and that will affect recrystallization. And recrystallization can be impacted by nano-voiding as well, and vice versa. The way the solutions are delivered is important, so your equipment is also part of this closed loop system. And as I said, it's a closed loop system. So once you're back to the beginning, it's just keep going around in circles. But we are definitely seeing benefits, and we have a much better understanding now of crystallography and factors affecting that within microvia structures. This is definitely the last slide. We've published a lot of stuff in the last 2 or 3 years. It's available publicly. If you're interested and you can find it, great. If you can't find it, please get in touch and we'll be more than happy to provide that. And with that, thank you for your attention, and we can open you up to questions.
Thank you a lot, Roger. It was a pleasure to hear you. It's time to proceed with our Q&A session. We received many questions, so I would like to remind you that we will cover as many questions as possible during this session, and all the rest will be answered by Roger after the webinar via email. So let's start. Which technique would you use to identify ELS layer if the recrystallization is complete?
The most reliable way to do it is use the TEM, so transmission microscopy. And ultimately, in our case, we usually use the nickel as the tracing element. If your bath doesn't contain nickel, you would have to look for the palladium in the activation system, and that would tell you where your electroless layer starts. And then knowing your deposition thickness, you could predict roughly where your electroless layer is. But TEM is the only technique we've found to reliably do so.
Thank you, Roger. So the next question is, how did you determine annealing 1 hour at 140 degree as the optimal condition?
It's not necessarily the optimum condition. It's just a condition that we know is sufficient to allow recrystallization to occur. You could use a higher temperature for less time. You could use 100 degrees and at least leave it there for a lot longer. It's a pretty typical heat treatment to enhance crystallization speed. But it's not necessarily the optimum one. It's just one that we use.
Thank you. So the next question from audience is, how does recrystallization depend on diffusion?
Ultimately, during recrystallization, what's happening is it's a grain boundary diffusion wave. So crystals will nucleate and then they will naturally grow out. Yeah. As part of that, there is also a degree of diffusion of the grain boundary structure. So that it's a diffusion-driven mechanism in terms of recrystallization. If your diffusion rate is very fast, you will get larger grains. If it's very slow, potentially you will get lots of smaller grains. So it's a direct physical property of speed of diffusion leading to crystal growth.
Okay, thank you. Does palladium layer below ELS copper play a part in bottom-up recrystallization?
Generally not, no. The density of that layer and the dispersion of it is so fine that it's generally insufficient to begin to pin that diffusion wave. So typically the diffusion path just goes straight through the seed layer, which is why we regularly see the electroless layers fully bottom-up recrystallized.
Thank you. So the next question is, how would one identify additives diffused from the bulk of ELS layer to the top?
That is a difficult one to answer, I have to admit, and I don't know the answer. I would have to get back to you on that one and talk to the colleagues in Berlin.
Good question.
Very good. I'll have to remember that one.
So the next one, is bottom-up recrystallization possible using direct plating systems such as EcoPact?
EcoPact's conductive polymer. In principle, I would imagine it would, yes. Any of the direct metallization systems which finish with an etch step essentially strip that DM system off the inner layer post and off the target pad. So you're still getting copper to copper adhesion. So I'm not aware that we've done any studies on it, but if your DM system finishes with an etch to the point where it cleans the target pad, yes, you should still get a bottom-up recrystallization, I believe.
Thank you. So the next question is the entrapment of hydrogen bubbles also a root cause of nanovoids, and how is it solved?
Entrapment of hydrogen. With hydrogen, hydrogen's a byproduct of the plating process itself. And as part of the reaction is the formaldehyde breaks down, creates the formate, and then you get the hydrogen breakout. And that is always going to be absorbed to some degree within the crystal structure of the copper, which will then disperse and come back out. Additions of nickel will reduce the levels of hydrogen absorption, but it doesn't completely stop it. And this is why in some cases, I believe it's quite possible there will always be a low level of nanovoids potentially. But as in all things with fracture mechanics, there is a critical level. And if you can stay below that level, they don't impact the failure mechanisms. So it's not a clear cut, hydrogen will disappear at some point, because currently I believe there's always a low level of hydrogen absorbed within the structure anyway.
Okay.
I'm not sure if that answers your question or dances around it, but if it doesn't, please get back to me.
Thank you. What cleaning process is recommended to ensure a clean and oxide-free target pad prior ELIS copper plating?
An effective one. There's a wide variety of cleaners available. There's combinations of acid cleaners and alkaline cleaners. You can use them individually, you can use them in combination. It depends ultimately on what you're trying to move. Grease requires an alkaline cleaner. Oxides work better with an acid cleaner. So it's a mixed combination. It's a case-for-case basis. It's not a simple use an acid cleaner, unfortunately. But typically the acid cleaners do work better because we're generally dealing with oxides at the base of microvias, if there's no residues from desmear anyway.
Thank you. So combined statement in the question. There are lithography steps between ELIS deposition and electrolytic plating. How would the wet-wet process integration look?
In that case, obviously you can't do that. The best you could possibly consider was if you did a wet lamination immediately after electrolysis, but this generally isn't practical. Most people are going to do dry film is a dry film again. If you're doing full pattern plating like that, direct to the electrolysis, you're going to have to do a wet, dry, wet. But if that's the case, the critical defect will be make sure that coming out the developers, you're not getting photomech residues, you're not getting dry film residues or developer residues or anti-foam residues, which is also the bigger issue. And then that your acid cleaning system really is cleaning suitably at the front end of your electrolytic plating tools. So yeah, you can't integrate a photomech process into a wet-to-wet, not easily anyway.
Thank you. So the last question of the session, how do you do the FIB in liquid nitrogen?
I was expecting that question, and again, I have no idea. It's our material science guys in Berlin came up with it. Again, I shall ask the question and get back to you on that one.
Okay. Thank you a lot, Roger. It's time to wrap up our webinar session. Thank you, everyone. We really appreciate you being here. Soon you will receive the replay link for this webinar. If you like this session, feel free to share the link of the recording, which will be available to view after the receiver registers. For our upcoming and on-demand webinars, please visit atotech.com/media/webinars. We will also keep you updated about our webinar schedule via email. Stay healthy and safe, and see you next time. Thank you.